Today, we're diving into a scientific detective story. It starts with the biggest mass extinction our planet has ever seen. And, believe it or not, it ends up at the very heart of our most advanced technology. It's a story all about one single, stubborn element that's both a tombstone for the dinosaurs and a building block for our future. For more than 100 years, this was one of the biggest questions in all of science. 66 million years ago, in what's really just a geological blink of an eye, something like 70% of all species on Earth, including, of course, the dinosaurs, just vanished. What on earth could cause such a catastrophic worldwide extinction? Well, it turns out the answer was hidden in plain sight the whole time, just waiting for the right detectives to find that one crucial clue.
And right here, this is the crime scene. All over the world, geologists kept finding this same strange, thin little layer of clay. Below it, in the Cretaceous rock, the world is teeming with dinosaur fossils. But just above it, in the Paleogene rock, they're simply gone. This line, the KPG boundary, is basically a geological tombstone separating two completely different worlds.
So what exactly happened at this boundary line? For decades, scientists threw out theories. Everything from volcanoes to climate change, but nothing quite seemed to fit all the evidence. The mystery needed a breakthrough, some kind of smoking gun. And this is where our detectives enter the story. A father-son team, Louis and Walter Alvarez, working with chemists Frank Asaro and Helen Michel. They decided to analyze this exact layer of clay from a gorge in Italy. And get this, they weren't even looking for the cause of the extinction. They just wanted to measure how long it took for that layer to form. But their routine measurement was about to completely rewrite our understanding of Earth's history. What they found was an element that had no business being there in such huge amounts. A cosmic fingerprint that pointed to a suspect that was quite literally out of this world. They found Iridium. And the sheer scale of this discovery was just stunning. We're not talking about a small spike here. The clay had up to 100 times more iridium than you'd ever expect to find in the Earth's crust. And this wasn't just in Italy. This same iridium spike was found all over the globe in that KP boundary layer. So why was this the smoking gun? Because iridium is incredibly rare on the Earth's surface. Most of our planet's supply sank down to the core billions of years ago when the Earth was still molten. But it's really common in asteroids and comets. For the Alvarez team, this couldn't be a coincidence. The conclusion was unavoidable. A massive, iridium-rich asteroid must have slammed into the Earth. The impact, which we now know formed the Chicxulub crater off the Yucatan Peninsula, was so powerful that it vaporized rock and the asteroid itself, blanketing the entire planet in a thin layer of dust and iridium. That was the exact same layer found at the KPG boundary. Mystery solved. But our story doesn't end in a crater. The same element that solved a prehistoric mystery has its own incredible story in the modern world. So what is iridium really? This quote really sets the stage perfectly. Iridium is tough. In fact, the very properties that made it the perfect geological marker, its incredible resilience, also make it a massive headache for modern engineers. The numbers tell the whole story. It's the second densest element we know of. A small cube of it feels shockingly heavy, almost twice as heavy as lead. Its melting point is way up there, over 2,400 degrees Celsius. And while it's extremely hard, it's also brittle. That means it shatters like glass instead of bending like steel. This is not an easy material to work with. So, to sum it up, iridium is basically the superhero of metals when it comes to durability. It resists corrosion and heat like almost nothing else. But its stiffness and brittleness are its kryptonite when you actually try to make something out of it. So, how do we take this impossibly stubborn element and shape it into useful components for things like high-performance spark plugs or crucibles for growing crystals? Well, that's the modern engineering challenge. Here's the central paradox. Its incredible strength comes directly from its atomic structure. But that same rigid structure fiercely resists being machined or shaped or welded. It's a classic case of an element's greatest strength also being its biggest challenge when you try to build with it. The structure of iridium is incredibly sensitive. Even tiny impurities can make it crack under stress. But paradoxically, engineers found that adding tiny controlled amounts of other elements like thorium can actually make it more workable. These additions strengthen the boundaries between the tiny crystals or grains that make up the metal, which help stop cracks from forming. This means the process is this delicate dance, purifying iridium to an extreme degree
and then adding precise microalloys to get just the right properties. To overcome these challenges, engineers have developed some truly innovative techniques, basically creating a high-tech blacksmith shop to handle one of nature's toughest materials. One of the cleverest solutions is to just not even try to melt and cast pure iridium. Instead, they use something called powder metallurgy. They start with iridium as a fine powder, press it into the shape they want, and then basically bake it at extreme temperatures. This process, called sintering, fuses the particles together without ever fully melting the material. Think of it like making a snowball just by packing it really, really tight. This method bypasses a lot of the problems of working with molten iridium. But what if you need to join two pieces of iridium together? That's where things get really tricky. The intense heat from welding creates stress in the material, and because iridium is so brittle, it's extremely prone to developing tiny, catastrophic cracks right in the heat-affected zone. Standard arc welding is often just too crude. It floods the metal with heat. The solution is electron beam welding, which uses a highly focused beam of electrons in a vacuum. It delivers intense energy to a very tiny spot, melting and fusing the metals so quickly that the surrounding area stays cooler. This precise control creates a stronger weld and a much smaller heat-affected zone, which is the key to preventing those disastrous microcracks. So let's bring our two stories together. From a thin layer of cosmic dust marking a global extinction to a critical component in advanced tech, iridium has a truly unique dual legacy. So here we have it, the two faces of iridium. On one hand, it's the silent cosmic dust that bears witness to the end of an era, the age of dinosaurs. On the other hand, its incredible resistance to heat and wear makes it indispensable for building the future, from the crucibles that grow sapphire crystals for our phone screens to the durable spark plugs in advanced jet engines. It's an element of endings and of new beginnings. This story of iridium really proves that even the most unremarkable materials, like a thin layer of clay, can hold epic tales of cosmic violence and planetary change. It makes you wonder, what other secrets are just hiding in the world all around us, waiting for the right person to ask the right question?